Air conditioning for big buildings. For most buildings, it is, of course, unwise to cool each of your spaces with a separate window unit. Why put a compressor and fan in each room when we might create a more centralized system? A centralized system makes for reduced energy use, fewer pieces of equipment to purchase and maintain, plus, fan and compressors are noisy, and the farther we can move them from the occupied spaces, the quieter those spaces will be. Air performs reasonably at carrying cold air, but water is better at heat exchange and does a superior job keeping cold over long distances. For this reason, many buildings, and some campuses or city districts, utilize chilled water. In this regime, pumps carry water chilled on the evaporator side, which is to say the cold side, of the compression refrigeration loop, to sometimes distant air handling units. The air handling unit then blows air across coils of chilled water, rather than coils of chilled coolant as we saw in previous examples, thereby cooling 70-degree return air to 50 degrees for distribution through ducts. The chilled water and coolant never touch or mix. They just exchange heat. To picture this, you might imagine a closed-loop pipe of coolant moving through a barrel of water, which is part of a separate closed loop. Similarly, on the hot side, we might increase efficiency and capacity by removing the heat in the condensing coolant with another separate loop of water. This condenser water is pumped from the condenser to a cooling tower, and water is allowed to cascade over a series of baffles, where the water is cooled by the outside air. When needed, an impeller fan can assist airflow across the cascading water. Some of the water evaporates and is replaced with new water, but most of it falls to a pool, where it is pumped back to the condenser. This distribution network using water is complicated, but not exceptionally complex. Let's review. Water is cooled by the evaporator and distributed to the air handling units to cool room air. A separate loop of water cools the condenser and carries its heat to the outside air via a cooling tower. You've seen cooling towers on roofs and adjacent to buildings, or as part of central chiller plants. The machine that does the compression refrigeration loop in this layout is termed a chiller. As we've seen, the recirculated air is cooled by the chilled water coil in the air handling unit, but that's a bit of a lazy simplification. In fact, we will use the air handling unit not only as a thermal comfort device, but also an indoor air quality device. Outside air is introduced into the air loop, and that outside air combines with recirculated air from the room before both volumes of air move across a filter. Of course, simply adding lots of outside air without exhausting some of the inside air is not stable. So exhaust fans release some of the portion of the stale interior air, that portion not destined for recirculation, to the outdoors. Exhaust fans often draw from lavatories, chemical storage rooms, machine shops, and other zones where used air is really not welcome to return to the building. Here we see the compression refrigeration diagram that we've been staring at, only in a more familiar setting. Water, chilled by the evaporator side of a rooftop chiller, the cold side, feeds air handling units, each serving its own floor. Simultaneously, a whole separate volume of water looping through a rooftop cooling tower cools the condenser side, the hot side. Now from the building section, we return back to the diagram. This is a good time to introduce mechanical heating, which is far more intuitive. For combustion, we require the usual suspects. I've drawn gas here, but it might be coal, or active solar, or oil. Either way, we need fuel, air for combustion, and a way to exhaust combustion air so that it doesn't make building occupants ill. The burning fuel heats water in a boiler, and that water is distributed, either as hot water or as steam, via another loop to coils in the air handling unit. In the cooling season, the chilled water loop is activated, but during the heating months, the hot water loop is activated. The boiler may also serve radiators, which are common on the perimeter of buildings where the mean radiant temperature may otherwise be quite low relative to the indoor air temperature. Economizer cycle. Buildings, especially in the interior of large structures, often require mechanical cooling even on very cold nights. This is because the heat generated inside the building by people, lighting, and equipment will offset some of the heat losses through the building envelope. In this kind of cold weather, you may be able to cool your building using the cold air outside instead of using traditional air conditioning. When you do this, when you cool your buildings using the free cold found outside instead of the compression refrigeration loop, it is said that you are using the system in a mode called the economizer. Here, we'll review two methods of doing this, so-called free cooling: water side economizers and air side economizers. In a water side economizer mode, cold air cools, and it really cools because it's winter, the water in the cooling tower. That cold water moves to the condenser side of the chiller and cools the coolant. The expansion valve opens, and this is important. The cooled coolant moves to the evaporator without fighting its way through the expansion valve. And there in the evaporator, it cools the chilled water. We've bypassed the compression refrigeration process entirely and still created chilled water for delivery in the standard way. This small change in the chiller, the opening of the expansion valve, actually prompts a fundamental shift in the very nature of the system. Without the expansion valve, there is no high and low pressure, no condensing or evaporating coolant, no state change, and no compression refrigeration loop. Rather, the chiller is transformed into a simple heat exchanger, an intermediary exchanging heat between the chilled water loop and the cold water coming from the wintertime cooling tower. Now, what you just saw is called a water side economizer because it relies on cold air to chill water. Like a water side economizer, an air side economizer uses the cold outside air to bypass traditional air conditioning in an effort to save energy. Why air condition when it's cold outside? In this case, in the air side economizer, it may be more energy efficient to directly introduce cold outdoor air to the inside so your equipment doesn't have to mechanically cool the warmer recirculated air. As a side benefit, this offers superior indoor air quality. All that fresh air replaces what would otherwise be mostly recirculated air. When in the economizer mode, often called free cooling, is deployed, technicians must be mindful that it isn't too cold. Coils in the air handling unit may freeze and bust, or ice may form in the cooling tower, busting that equipment. Often an economizer cycle is not included in a mechanical package when it really should be. It is free cooling, and even when the economizer mode is available, it is often underutilized by building equipment technicians. That's why it's vital to have the architect, the mechanical engineer, the owner, and the building technician at the table together at the beginning of the design process to get everyone nodding their heads in agreement toward a common goal.